everyone, we will be looking at C2Br4, or also known as tetrabromethylene, today. We will be learning its Lewis structure, molecular geometry, its electron box diagram, and its contour diagram. Starting off, we have to draw its Lewis structure in order to know its molecular geometry. So to do this, we have to find the total electrons that should be in that structure. We know that carbon has 4 valence electrons, and there are 2 of them, so we have 8 electrons for both carbons. We also have to find bromine, and bromine has 7 valence electrons, and since there's 4, we have 28. So the total, by adding 28 electrons and 8 electrons, would be 36 electrons. Since I have already drawn out the Lewis structure, I can figure out how many electron pairs are around the central atom, which is carbon right here. So we know that there's 1, 2, and 3 electron pairs around the central atom. So 2 bromines and 1 carbon. Now that we know that there are 3 electron pairs around the central atom, which is carbon, the electron geometry for this is trigonal planar. And the molecular geometry for this is also trigonal planar. So since we know it's a trigonal planar shape, we know its bond angle, which is 120 degrees between the 2 bromines. Since we know the geometric arrangement, we can also determine its hybrid orbital, and its hybrid orbital in this case is sp2. As you can see here, we have 2 pictures of tetrabromethylene. We have the atomic orbital, and we have the overlap of the atomic orbital. So in this first picture here, we have our carbons and we have our bromines. We can see the double bond in this picture, and we could also see that there is a pi bond here and a sigma bond here. Not only there's a pi bond and a sigma bond between the carbons, there is a sigma bond between the carbons and the bromines. So now we have our pi bonds between carbon and carbon, our sigma bonds between carbon and carbon, and 4 of our sigma bonds between carbon and bromine. So in this second picture, again, our carbons and our bromines. So carbons, bromines. You can see its overlap, and you can see the hybrid orbital, which is our sp2 hybrid orbital. We learned earlier that tetrabromethylene is trigonal planar, and it's trigonal planar for both its electron geometry and its molecular geometry. Because its molecular geometry is trigonal planar, we know that the bond angle, again, as we previously learned, is 120 degrees. We also know that the bond between carbon and carbon is a double bond, and this does not change the 120 angle in the trigonal planar, so the angles between carbon and bromine here is still 120 degrees. So these are just other pictures of tetrabromethylene, and it's just to see if there's any lone pairs or free radicals that would affect its bond angle, which again is 120 degrees. If there were any lone pairs or free radicals, we can have an example. So let's say SO2. So S would be our central atom, and O's would be there. Making sure that every atom fills its octet. we can see that this here is our lone pair. So this will like push down and it will create an angle that is less than 120 degrees. This angle happens because lone pair, bonding pair, repulsion is greater than bonding pair, repulsion. Sulfur dioxide is just a brief explanation of what would happen if a trigonal planar has a lone pair or a free radical. Back to our original molecule, tetrabromethylene. These pictures are actually great to show its shape. It's showing that there are no wedges or dashes when we draw the Vesper structure. So again, it's just, flat, it's on a plane. This is just like the side view of C2Br4. So we can review again that this is trigonal planar. It is 120 degrees. We have our pi bond and our sigma bond in between the carbon and carbons. And we have our sigma bonds between the carbons and our bromines. Right now, we're going to be drawing our electron box diagram for tetrabromethylene. So starting off, we are going to write our ground state for just carbon. We can see we have our periodic table right here, and we know that carbon is in period 2, so we have our S and our P block, correct? So there are going to be 2 electrons in the S orbital, and there are also going to be 2 electrons in the 2p orbital. We have to keep in mind that we do have another carbon to bond to the carbon that we're drawing here for its box diagram. And we do have another pair of bromines. So what I'm going to do is that we're going to promote an electron from the 2s ground state to the 2p excited state. And I'm just going to fill in my electrons in the excited state. And again, we need energy to promote an electron. So our goal is to reach its bonded state. So before doing all of that, we first have to hybridize our electrons in the excited state. So we are not going to hybridize all of the electrons in this excited state because we are only dealing with sp2. So what I'm going to do is circle the 2 electrons in the 2p and the 1 electron in the 2s. We also have to show our arrow that we are hybridizing these electrons. Next, we're going to use the electrons that we hybridized to fill in the sp2 orbital in the bonded state. You can see that this sp2 orbital is in between the 2s and the 2p. We still have 1 electron in the excited state, which will be here in the bonded state. You can see that it's still in the same level where the 2p is in the excited state. So right now, this is our carbon. Since this is our carbon, we have to bond our carbon to 2 bromines. We know that bromine is in the 4th period, so we're just going to write it here above the carbon that we drew. We know that it is 5 electrons in the 4p. 4p. So what we're going to do now is we're going to bond the non-bonded electrons in bromine and the sp2 orbital. So we have this and we have this. So now we have our sigma bond between our carbon and bromine. We have only bonded the bromines with the sp2 orbital. We have to remember that we still have another carbon and we still have another pair of bromines. I have already drawn our carbon here, so that's our other carbon. So other carbon. Again, we're going to bond our bromines with the sp2 orbital in the other carbon. And again, we have our carbon-bromine sigma bond and our other sigma bond right here. The next step is we have to bond our carbons with one another. So what we're going to do is bond our electrons that are not paired yet with the sp2 orbitals. And then we're going to bond our electrons in the 2p orbitals in both carbons. This right here that I circled in pink is our double bond. So we have our sigma bond. Let's see if I have space. We have our sigma bond between carbon or carbon and our pi bond between our carbon and our carbon. Right now we're looking at a rough model for C2Br4 that I created with a model kit. It's pretty rough because we don't have our double bond between our carbons, and it's not as great as the pictures that I've shown you previously that showed the overlap of the atomic orbitals. As said before, we have our pi bond, our sigma bond here, 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 and here. Again, this is trigonal, planar for both of the electron geometry and the molecular geometry. Since it's trigonal planar, again, we know that the bond angle is 120 degrees. Since we finished our box diagram for C2Br4, we can finally draw our contour diagram, which I've drawn already for you guys. You could see that a sigma bond forms between the 4p orbital and the sp2 orbital. And you could also see the sigma bonds between the sp2 orbital of the carbons and the pi bond between the 2p orbitals of the carbon. We still do need to include that this has a 120 degree bond angle. It is shown in this contour diagram that there are no free radicals or any lone pairs, meaning that this diagram only shows bonded pairs. So right here would be a bonded pair. As I've said previously, if there were bonded pairs or any free radicals for trigonal planar, it will affect the bond angle of the molecule, making it less than 120 degrees because of the lone pair bonding pair repulsion is greater than the bonding pair repulsion. To sum this up, we now know that this molecule is trigonal planar for both the electron and molecular geometry. Its hybrid orbital is sp2, and its bond angle is 120 degrees, and there are sigma bonds for between carbon and carbon, and a pi bond between carbon and carbon, and as well a sigma bond between each of the carbon and bromine.